I am going to attempt to teach you 5-2 so we don't get too far behind. Let's see how this goes. Okay, so in 5-1, we were just getting started, and we were talking about how to find the area under the curve, such as, let's say, that. Okay, we divided it into X amount of rectangles. Let's say we want to have that many, so that's 1, 2, 3, 4, 5, 6. Okay, so we said let's do 6 intervals. Let's find the area of each of those rectangles, but before we can find the area, we need a length times width. I have no idea why that stupid eraser thing is here, but anyway, length times width. Of course, the width is predetermined. That would be the change in X right here. Okay, let's try to see if we can get rid of that. Okay, and all right, then the height we could do different ways. We could say, all right, we could do a right endpoint, and then say, all right, whatever this height is, that's the length of the rectangle, and the width is that change in X. Okay, we also did a left endpoint, maybe. Okay, where we use the left endpoint right here to figure out the height of the rectangle. We also did a midpoint. Let's say we want to use the midpoint here. That's not really the midpoint, but anyway. And we said, okay, let's find the height of that. We didn't do them all three. We did one or the other. So once we did that, we said, all right, the area is the length of width. And we said, oh, let's find the area of all the rectangles. By using, oh man, that's really annoying. Using the length times width. Okay, and then add all those areas together. That area, there we go. Come on, I knew you were missing those sound effects. That area would be close to the area that we were looking for, which is the area under the curve. Okay, so we're going to introduce just a little bit of different notation, and remember we called that, I guess we called it R5 if we used the right endpoints. We called it L5. If we used the left endpoints, we called it M5. 5 meaning we had 5 intervals, right, left, midpoint for the height of the rectangle. Okay, so we're going to kind of go on to a new notation, and notice it starts out looking the same, except it's S as in sum. Okay, I don't know what's happening with that circle thing, but okay. N would be the number, and of course that would match here and here. So in this case, N was 5, because we talked about 5. So this one would look like I equals 1 to 5. For summation, we learned this in pre-cal, but we usually start with 1 because then we can just count 1, 2, 3, 4, 5, and that's 5 of them. And then f of xi, whatever the x, f of x times change in x would be length of the rectangle times width, or vice versa, however let's have it. Okay. All right, this is referred to as a Riemann sum. Okay, and what we do is we're going to change that n so that we're going to have, you know, well, let's say, depending on your function there, maybe your n, if your number of subintervals increase, what happens to n? Well, n increases because n is the number of subintervals. And if n increases, say, instead of 5 now, let's go to 10. Okay, well, what the heck? Why don't we just go to 100? Okay, now I'm not going to attempt to draw 100 spaces in here, but what's going to happen is you are going to have less space in between. If you divide into tiny little rectangles, you're going to have less space that the area doesn't cover. So then that means as we get closer, as we get, you know, what the heck, let's go to 1,000. Your area is going to get closer to what we would call the real area under the curve. And that's what we're after, the real area. And we can find this using calculus. We just got to inch up to it. Okay? All right, so next page we have an example. Random green hair. Okay? And we are going to evaluate the sum. We're starting with a linear equation here. And we want to go from 0 to 10 with 5 subintervals. So what I've done here already is I've graphed this linear equation. Remember, here's your intercept. Okay, we went down 2 over 5. We're over here at 5. We went down 2 and over 5 again. We're supposed to be at 10. Okay, so if we want 5 intervals, right? So that means we get 10 divided by 5. That means every 2 thing we'd have an interval. So let's go to 2 and 2. Okay. And then it says to use the left endpoint. So on the left, we go here. Left, we go here. The left, we go here. I'm a little off, but okay. So I've got this done over here in little color coded. So let me just pull that around here. All right. So this is what you've got. And you're going to do, it says to evaluate the Riemann sum. So the Riemann sum says we are going to do I equals 1 to 5. They told us to say 1 to 5 of f of xi times the change in x. Okay, so this is technically S5. A summation, remember, is just another way of writing a sum. Okay, so we're going to take, remember we did the left endpoint, so on the left is f of 0 times the change in x, remember we said was 2. The next f of 2 times still f, okay, f of 4 times 2, f of 6 times 2, and of course I have to squeeze, f of 8 times 2. Okay? All right, now you can do one of 2 things. You can either get those values of these functions right here. Let me try it. My color has not been working very well. Let me try these function values we can get off the table, or we can just plug them in, whatever's easiest. But for now, we're just going to get them plugged in. You can see I've got y equals negative 2x, 2/5 x plus 4 in my calculator, and I'm going to pull up the table so we can get our values quickly. So here we go. Second graph would give us our tables, and we need 2 8s. So I'm going to just pull up, let's see, 7, 8, because 0 is easy. Okay, so if we plug in a 0, get these over here, you are going to, of course, get 4 times your change in x. F of 2 says it's 16/5 times 2, your change in x. F of 4 is 12/5 times your change in x. F of 6 is 8/5 times your change in x. And f of 8 is 4/5 times your change in x. Okay, we're going to add those together. So we'll just pull up our calculator here again, so you know what we're doing here. And we're going to say 8 plus 32/5 plus 24/5 plus 16/5 plus 8/5. Okay, it's 24. Now remember, we were supposed to have 5 rectangles. So there's 1, 2, 3, 4, 5. You always just double check. So we get 24. Okay, so that's the area of the sum. Now, this is a triangle, basically. So let me try if you took, remember this is your triangle. It's a right triangle. So this basically is base height divided by 2. The base is 10, of course. Area of a triangle is 1/2 base times height. Base is 10. Height was 4. 40 divided by 2 is 20. So this is the actual area. Okay? Because we can do that because it's a triangle. This is our approximate area using calculus. But look, we've got some, if we look at the actual area that we found, we have some extra. And that's that stuff. That would account for that 4 extra from the 20. That's how you do Riemann sum. Okay, now the correct answer to the Riemann sum is 24, not 20. 20 is the correct answer to the actual area, but that's not what we're after right now. We're actually after the Riemann sum. Okay, so moving right along. We're going to say, well, wait a minute. As we approach, as n approaches infinity, okay, we are going to call S of n, and this is the Riemann sum, okay. As we get closer and our n's get bigger and bigger, we're going to say this is the same as this. Okay, how do you say that? It's the definite integral. It's called the integral from a to b of f of x dx. You don't say d times dx, you just say f of x dx. And remember, the change in x here is going to be what the difference between the big minus the little over however many you want, just like we've done it in the past. So if you look at the last page, remember n, we went from 10 to 0, so b, this was b, this was a, 10 minus 0 over 5, that gave us our 2 for our change in x. So it's what we've been doing, we just hadn't talked about it right that moment. Okay, so we are moving from the Riemann sum to the definite integral, and we are going to talk about some rules for just integrals in general. Okay, so right now, y equals f of x is non-negative. So remember, that means f of x here is above the y-axis. Okay, this is f of x. It's not down here, because then that would be negative. Okay, all right, so, and it's integrable. Now, you don't know really what that means, but that means you can find the area right now. Let's just say that. Okay, so it says if the area is non-negative, so let's say it's that, okay, and here's A, here's B. A is the area under there, and A is the value of the definite integral, okay? So A is the area. Forget that. Okay, area. All right. So this is moving on to exact area now, and we're going to find, we're going to use the Riemann sum for a while, but eventually we're going to move away from the Riemann sum and actually find the area using the calculus. Okay, so what if y is negative? As in it's like this. All these y's are negative. This is a negative whatever, this is a negative whatever, this is a negative. So that's what that means. Y is negative. Okay, so what happens is if we want the area again, we're just going to take the opposite of what we get. So this is your regular integral, and you're going to say, wait, I don't want a negative area. I really want this to be positive, so we're just going to take the opposite of it, and that would give our value, our area, a little bit more credit, because you don't really want a negative area. Okay? All right. What if we have both positive and negative area, such as that? All right. Then what we want to do is we want to add the area above the x-axis, and then we want to subtract the area. So that will make this give us a positive value. Okay. For example, let's say the area, just picking out numbers here, let's say the area is 15. Okay, just a nice number. And this area looks like it's about 14. If we wanted to know the total area here, which is what we're after when we say area, is total area, right, for now, we're going to say 15, and then we're going to say minus negative 14. And then that will give us the 15 plus 14 that we want, which is the 29. Okay. All right. So those are the 3 rules about positive and negative area that you need to look at. Okay. Now, we're also going to use some geometry. Now, remember in that one we had, I did use geometry. I did base times height divided by 2. Okay. So that was because it was a triangle. All right. Well, let's take a look at this. I'm thinking that this is not going to be a triangle. Okay. Well, while I'm pulling it up, what do you think it's going to be? Any guesses? Well, it's going to be half a circle. Now, here's the thing. You're going to have to recognize this because, let's see if it'll graph it. It's half a circle. Okay. Let me change my negative. My radius is 4. So let's go, 2. Let's go, so we can spread it out a little bit. And let's do the same thing for this. Negative 5, 2, 5. Okay, there's your top half of your circle. All right, this is negative 2. Stop. Hello, why did we do that? Negative 2. Oh, here we go again. Okay, so, darn it. Okay, let's try this again. My pen was acting up. Okay, so you've got a half a circle that starts at negative 2 to 2. So remember how to find the area of a circle. It's pi r squared, but we only have half, so we're going to do half because it's half of the area of the circle. Okay, what's the radius of the circle? Looks like 2, so 2 squared. 2 1/2 of 4 pi would be 2 pi. Okay, so this is the exact area of the integral, the exact area of the circle, and also the exact value of your integral. Okay, so we have the Riemann sum. That's not the exact value yet. We have the geometry that if it works to use a geometry, it would only work in your basic shapes. Okay, the ones you already know. So geometry only works using basic shapes. If it doesn't have a basic shape, then we can't use geometry. Okay. All right, so we got some properties here. Let's see how this goes. Okay, we have, these will look like limit properties a little bit. They'll probably remind you of that, but that's kind of how it is. Okay, so if we have a, and this is just one illustration, it's not every single illustration. So let's say we want to look at the integral from a to b of c. Now remember, this is the function y, or f of x equals c, which is a horizontal line. Okay, so there it is, y equals c. Okay, so you did that and you cut it off from a to b. So basically this is the area that you're looking at. Okay, so it's a rectangle. So basically we're using the c, which is the length or width, whatever you want to call that, of the rectangle right here. And then whatever this length is the width, and that's how we find that. Okay, so that's basically using geometry. Okay, so this is probably something that you need to remember for a while until we do something else with it. Okay, so the c is multiplied by whatever this number times minus this number is, because that's the length of the integral. Okay, this looks like it is the integral of a sum is the sum of the separate integrals and the difference, or the difference of the integrals. Okay, so that's just like the sum of the limits equals the limit of the sums, blah blah blah. Okay, so basically if I want to say a to b of f of x plus g of x dx, that's the same as doing them separately. F of x dx minus a to b g of x dx. Okay, this one is c times your f of x. Again, it's like your limit. You can pull that out and then do your integral separately. Okay, this is from a to b, but notice now we switched it around so we would negate it. Okay, and this is from a to a, which means we're not moving, which means f of x, there's no integral, there's no value. We're just stuck there at a. Okay, let's look at some examples here. I'm not going to show you this program yet, so let me pull up some examples and let's stop. Okay, so example, let's look at number 9. Okay, on page 354. Okay, so we're going to do where it says to use the midpoint rule with the given value of n to approximate the integral. So your problem looks like this. You're taking the integral from 2 to 10 of x cubed plus 1 dx, and it says n equals 4. Okay, so here's what you're doing. You're doing basically M4 from before. I equals 1 to 4. That's what they told you. All right. Cube roots of x cubed plus 1. It's not x plus 1, by the way. Change in x. Okay. All right. So we're going to do midpoint. We want to pull it up on the calculator. I always like a visual, you know. Square roots of x to the third plus 1. Okay, graph it. Looks like that. All right, we are going from 2. Oops, that's not a good. Let's try a different. We're going from 2, so I'm going to do 0 just for a visual. 2, 11. I'm going to go really past the 10. And then let's see what this looks like. All right, graph it. It's getting chopped off here, so I'm going to make that That's going to be at 0 because it doesn't look like it went under. And let's try this under here at 50. And graph, see what it looks like. Okay, perfect. Now, no. This thing's persnickety here. All right, so we're going to use this one. Okay, and here's 2. And 2 right there. And here's 10. Okay, so we're looking at that. That's what that means, this area under here. All right, so since we have it on the calculator, we can use, or do we? We can use the table. And we're going to do, we have 4. So let's figure out first here that 2 to 10, which is change in x, we're figuring out change in x, come on, is b minus a over n. Okay, remember this is a, this is b, and there's n. Okay, so 10 minus 2 over 4 is 8 over 4, which is 2. Okay, so every 2, we're doing midpoints. All right, so we're going to figure out which midpoints. So first, get rid of this stuff in here so we can draw some lines here. Try and get this a little bit bigger. Okay. What that is, let's get rid of that. Okay, well, all right. So we're starting with 2 and going to 10. All right, we're every 2. So 2, 4, 6. Okay. Now, but we're doing a midpoint, so this actually is our height that we're going to use. This is our height. This is our height. And this is our height. All right, this is 2. This is 10. 4, 6, 8. So our midpoints are 3, 4, 5, 6, 7, 8, 9. All right, so we are going to do the f of 3 times that change in 2, f of 5 times the change in 2, f of 7 times the change in 2, f of 9 times change in x, which is 2. Okay, and then you're just going to look up all those values or plug them in and then get a total. And remember, the total area would be, including this, which is extra, and discluding this. So it looks like, honestly, we're going to be pretty close to the actual. Okay, we don't have any way of doing the actual at this moment, but we're doing the integral in terms of a Riemann sum. So that's how you do number 9. Okay, okay, and then they're going to also let you change limits to integrals. So just write those out. Let's take a look at number 31. Okay, it has a graph of f, and it says evaluate each integral by interpreting it in terms of area. So this is when we're going to do the area that we talked about. Okay, I'm going to do a very bad, it goes something like this, straight over, down, and up like this. Okay. So this is number 31. It says, part A says, we are looking for the graph from 0 to 2 of the integral from f of x, 0 to f of x dx. Okay, now the dx, remember, is just been replaced from the Riemann sum of the change in x. Okay, and in your graph, 2 is right here. Okay, so basically you are looking for this area for part A. Okay, now what does that look like to you? To me, it looks like a trapezoid. Okay, so 1/2 h b1 plus b2. All right, remember your bases are your parallel sides, so that's this is base 1, this is base 2, that's 2 up. You can tell this by the graph, but that's up at 3. This is up at 1. So 3 plus 1, the height would be right here, which is 2. And then you would find that. So that's how you do in terms of area when the graph is already there. Okay. 41 and 41 through 44 using those properties that I gave you. Let's just take a look at number 40. Okay. It says, given that the integral from 0 to 1, come on, of 3, oh, here we go again. Okay, stop. Okay, we're going to try 41. All right, it says, write as a single integral in the form a to b f of x dx. Okay, right, here we go. As, come on, a single integral. Okay, and that's the key. All right, so here we have from -2 to 2, f of x dx plus 2 to 5, f of x dx minus -2 to -1 f of x dx. Okay, as you can see, we got 1, 2, 3, and we're supposed to write as 1. Okay, so I'm trying to figure out, remember, these are all in terms of area. This is all talking about area. So I'm just going to kind of organize myself. I've got from -2 to 2 covered by, let's call this A, area A. From 2 to 5, let's call this B. And then we're subtracting -2 to -1. We'll call that C, and I'm going to put that in a different color, maybe. So that -2 to -1 would go like right here. Okay, so what you want to do is use your properties and say, okay, I can put these two together and make -2, since they're both the same thing, to 5 f of x dx. Those two are together. That's using the property of a to b of f of x plus b to c of f of x. Okay, so that's that. And then we need to take this away. If we're going to subtract from -2 to -1 f of x dx, okay, that means we've got -2 to 5 covered, but then that's all this area. But then we want to take this away, which means we'd only go from -1 to 5, because we took -2 to -1 away right here. We took this out of here. So that means we're only starting at -1 to 5 of f of x dx, and that's the answer. That's how we've written it in terms of a single integral. Okay, so here's what you, sorry, I keep showing you that. Here's what your homework, here's what I want you to try. Page 353 continue. I want you to do 1, 2, and 9, 17 through 20, 31, 32, 41, through 44, and number 47. Okay, good luck. Thanks.